This lecture is on evapotranspiration, and evapotranspiration can be an extremely deep mathematical scientific concept. People have worked for decades trying to work out the perfect mathematical models and devise ways to combine weather data of all sorts and plant data and determine how to best measure the evaporation and transpiration from a given crop. So there's a lot of, I would say, controversy as well as research and different opinions about it. But for the average grower, it's not really that big of a controversial topic. The average grower, you pick your model and run with it. And there's a lot of good information there. So the PowerPoint I'm going to present to you is one that I found available online, and it's available to the public. So I'm using it rather than reinventing the wheel, but I shortened it dramatically. So you see here is the long version, excuse me, and then the version I'm going to give you. If this information is interesting to you, feel free to go through the long version and compare that to what I provided you and see what kinds of information I did cut out. There's some great papers and great information on evapotranspiration. So that said, we're going to talk about the concepts and how it feeds into one piece of the data puzzle for irrigation management. And so there's two major processes going on to calculate evapotranspiration, and that's the evaporation of water from the soil surface, which certainly is impacted by things like mulches, how you till the soil, the type of soil, the amount of compaction in your soil, whether you have weeds or cover crops covering the soil, solar exposure, whether you're south facing, north facing, etc. All kinds of things can impact the rate of evaporation from the soil surface. In addition, you have transpiration from the crop. So evaporation is water that turns to vapor, gas, and it goes into the atmosphere directly from the soil surface, but transpiration goes through the plant, and it's still liquid water in the plant that turns to gas, but that's occurring almost exclusively in the leaves, to a small extent the stems. Depends on the plant. If it's a cactus, it's mostly the stems, but because they don't have much transpiration through the leaves because they only have spines for leaves. Anyway, off that little side diversion, it is water going through the plant. And the evaporation process inside the leaves of plants, exiting through the stomata on the underside of most leaves, that is transpiration. And that is going to also be impacted by, well, what plant is it? What stage of growth is that plant? And how much plants are covering per acre? How healthy is that plant? How fast growing? How are the cultural practices of fertilizing, etc.? So that is the two things we're looking at: the water lost by evaporation plus the water lost by transpiration. Now you can also lose water by leaching, but that only occurs when water is going down past the root zone and continues down into the deeper depths of soil, eventually to make it to the water table down below. But that only occurs during rain events that add enough water to the soil to go beyond soil water holding capacity, or if you irrigate beyond the water holding capacity of the soil, again, pushing the soil moisture down past the roots. And with some minor exceptions, the water doesn't come back up much. it goes down and keeps going down. We're not talking about water loss to leaching. That's something you have to account for other ways. So when you look at an irrigation event or a rain event, you don't look at the total amount of water that was added. You stop counting water once you reach field capacity, because any more water that goes on is going to leach. There's also runoff, and you don't want runoff when you're irrigating. A well-planned, well-designed irrigation system, you're not going to have runoff. But the reality is some percentage you do potentially have runoff, less with drip irrigation, more with sprinkler and flood irrigation. But that runoff is lost water that isn't going to make it into the plant's root zone. And we try to avoid that with irrigation, but we can't avoid it during rain events that are sufficiently large. So again, we don't count runoff. That is a different process. We're only talking about the water that is there at field capacity or less that is going to leave through these two processes. And those are the two major processes we're concerned about when trying to manage irrigation. So evaporation is the process of the liquid water turning into water vapor, a gas. And there's a lot of energy involved in that. And evaporation is the predominant component of evapotranspiration when the crop is very small. You've got much more soil exposed, much less crop. So when I first plant a field of lettuce or whatever, the lettuce plants are just these tiny little sprouts, and they aren't transpiring very much because there's not much plant there. So most of the ETO, or the evapotranspiration, is evaporation. But as the plant gets bigger, the percentage of the evapotranspiration that is transpiration keeps going up to a certain point, and it can start going down after that certain point. We also have evaporation under high frequency wetting, when the soil evaporation and evaporation of free water from the plant surfaces can be high. So if we're constantly watering and the soil surface is really wet, if we're sprinkling and the plants are really wet, we can actually lose a tremendous amount of water to evaporation under those circumstances as well. So there can be certain things that need high surface moisture in certain kinds of grasses, in certain environments, like heavy overhead water, maybe not huge amounts of it, but frequent. And so when you constantly have lots of water available to evaporate on the surfaces of the leaves or on the surface of the soil, evaporation is much higher. Transpiration, the vaporization of liquid water in plant tissues, and the vapor removal to the atmosphere, primarily through the stomata on the underside of leaves. There are other pores as well that we haven't talked about, like lenticels, which predominate on the shoots, but we really don't have nearly as much water going out through these tiny lenticels versus the leaves, the stomata on leaves. Vaporization occurs in the intercellular spaces of the plant tissue, while exchange with the atmosphere occurs through and is controlled by plant stomata. Transpiration is predominant once the crop has developed and the canopy shades more and more of the surface of the soil, that is. So those are the two components defined. So what affects transpiration, evapotranspiration, excuse me? Weather, and weather is a number of different things: solar radiation, wind, temperature, relative humidity, soil temperature. Those are some of the main ones. The crop characteristics. Are we talking about a vineyard? Are we talking about 80-inch beds of iceberg lettuce? Are we talking about baby leaf spinach? I mean, there's a ton of different things. And at what stage growth is it? How healthy is it? All sorts of things. Management practices, so how you handle your soil, your weeding, your fertilizing, etc., and other environmental conditions. So weather, the main ones, as I mentioned a moment ago, solar radiation, a measure of how much sun is hitting. So we don't have to look at all of the solar radiation characteristics, which would include how cloudy is it. If we're just measuring how much sun is hitting, cloudiness is going to directly impact that. So we don't have to measure it in a bunch of different pieces. On long days, during the summer, when the days are longer, we're going to get solar radiation for more hours of the day versus the fall and winter months where the days are shorter. And when it's cloudy, we're going to get less solar radiation. When it's clear, we're going to get more solar radiation. So we can measure that one fairly straightforward and easily. Air temperature, also super easy to measure. Relative humidity, there's a number of different ways to measure humidity, but they are just a measure of what percentage of the potential water that the air can hold is actually in the air at a given moment, the percentage of the capacity. The warmer the air is, the more water vapor it can hold. And warm air can hold a lot of water vapor. It's amazing. In a warm room, there can be a very large amount of water floating around in that room compared to what you might think. The cold air, on the other hand, can hold very, very little water. So it's not a matter of how much water is in the air, but how much is in the air as a percentage of what the air can hold. So if you have a cold air, it can't hold very much water. But if it's only 50% humidity, even if it's cold, there's still room for water to evaporate. There's room for moisture to vaporize into the air. So the percentage is the relative humidity. It's relative to the temperature. The percentage of moisture in the air is relative to the temperature of that air. And then wind speed. The faster the wind, the more it carries away water, the faster things evaporate. Now, soil temperature is also important in this equation. That's not listed here. Crop characteristics, height, roughness, stomatal control, reflectivity, ground cover, rooting characteristics. Again, if we're talking about Bermuda grass versus prickly pear cactus versus pine trees, you know, every type of crop has its own characteristics that are going to have massive impacts on how it uses water. So every crop is different, and we learn about our crops in terms of what its typical water characteristics are, and based on what we're growing and the varieties and our management techniques, we can tweak those numbers a little bit. And the stage of development, if it's very, very, very young and small, it has less transpiration occurring. At the larger stages where it's got more ground being covered by the canopy of that plant, it has more transpiration. The faster it's growing, the more transpiration. And it reaches a point where it's reaching the end of life, perhaps, or end of season if it's a perennial, and it slows down as well based on time of year. Management, how you irrigate, not only the management practices of irrigation, but whether you're doing drip, furrow, flood, sprinkler, whatever. Your cultural practices, fertilization, pruning techniques, planting spacing, all kinds of things, fertility management, disease and pest control, and on and on and on and on. Just everything you do impacts the plant's growth rate and size and everything that will impact how much water it ends up taking up. Environmental conditions, soil type, texture, water holding capacity, soil salinity, soil depth and layering, poor soil fertility, soil exposure and sheltering. So if you're in the direct sun, a south-facing slope, a north-facing slope, shaded from adjacent trees or a hillside or something, all kinds of things that go into it. So you don't have to memorize all of these things on these last slides. Most of it's pretty common sense if you get the major categories, and you could probably think off the top of your head some of the things that are important with evapotranspiration. The list is rather long. So once we know that there's lots of things that all go into this equation of calculating evapotranspiration in the real world, we know we can't measure all of those things and have a good estimate for all of those things that we listed on those previous slides. We have to narrow it down to things that are more manageable, easier to measure, more numerical, like relative humidity and temperature and solar radiation. Those are easy to measure. We can stick a number to it and come up with these estimates and use those estimates based on a mathematically achieved model. Now we can directly measure evapotranspiration, but that's really expensive. And there's a device called a lysimeter that I'll show you in a slide coming up. But the direct measurement is not practical unless you're doing serious basic research. So the only people I know who have done direct measurements are universities or businesses that have collaborated with universities on a long-term research project. So instead of doing that, agricultural professionals use a computer, and they compute evapotranspiration using data that's collected from the weather, which is what we call empirical data or numerical data, and some that's semi-empirical, like you could maybe say the percent ground cover of a crop. It might be something that goes into your equation, and you might just be estimating it. You're putting a number to it, but you're kind of estimating or guesstimating. And there are programs now where that can be tied in with aerial photography to give you pretty accurate numbers, but it's not quite as solid a number as temperature, for example. And there are also crop growth estimates and things like that, which you can sort of put a number to it again, but what stage of growth is not something that you have a hard fixed number. You approximate it based on some growth curve or other information. But you put all of this together, throw it into a computer, and it will come back and say, all right, based on the data you fed me, we lost 0.13 inches of water out of the soil today. A little over a tenth of an inch, 0.13. So, you know, that's just a number I threw out. Could be any number within reason, but that's what the mathematical model does. So I mentioned direct measurement is very challenging and expensive. It does use a type of science called lysimetry, using a lysimeter. And you literally are measuring the amount of water lost by measuring the mass or the weight of a very large sample of soil. And there are also energy balance methods I'm not going to get into, but very interesting direct measurements that if you want to look up the Bowen ratio or the eddy correlation and you want to look at these micrometeorological methods, go ahead, but that I'm not going into it on a test. Lysimetry, you first take your crop of interest and it's grown under natural conditions in an isolated tank in a large field of the same crop. So you somehow set up this tank that is as close as possible to the natural conditions of the field, but the tank is basically on a big, massive scale. And you're measuring everything that goes into that tank, all the water, and you're measuring the mass, because you're also gaining weight, not just by water that's being added and losing weight by water that's being lost, but you're gaining weight from carbon dioxide being turned to sugars and proteins and other things as the plant grows. So you have to measure biomass, or how much plant material is there, after drying it out and removing the water. So it's very complicated. You do need to put these things together very, very carefully. And there are many types of lysimeters, some that actually look at drainage, some that look at water table issues, but the weighing type is the only one I've ever had any experience with. You could look up different styles. They all have their pros and cons. They all have advantages for trying to estimate. So here we've got a couple of pictures of lysimeters that are out in the field, and it doesn't look like much. It's just, you know, it looks like something that's laid out with a couple of borders here. And if you look carefully in the grass, there's a couple of borders on the grass. It just looks like somebody put up these little tiny mini barriers, but it really goes down deep into the ground. And so you set up these lysimeters that can give you extremely accurate measures if they're set up correctly. So here's another lysimeter, and you notice right next to the lysimeter there's a weather station with an anemometer for wind, or actually a weather vane and anemometer for wind direction and wind speed. This is probably measuring temperature in here, and maybe humidity. Solar radiation is, I'm sure, on here somewhere, excuse me. And then this whole thing is the lysimeter. And what are they measuring? Can't tell you for sure, but this might be some sort of forage grass in some sort of a livestock grazing environment, to look at the water profile in some sort of a pasture land for livestock. What does it look like in cross section? Here we have this black outline is a hole, a trench that's been dug. And underneath there is a big tank carrying your soil. And all of this tank is sitting on a scale. And there's a tipping bucket collection for any water that drains through. You need to be able to not only measure the water that is going in by the change in mass, but you also, if anything leaches, have to take into account that. So here's a device that's measuring any water that leached and drained off the bottom. And this tipping bucket measures exactly how many ounces of water or milliliters of water have drained through leaching. And that is taken away from the calculation, because even though that's part of the water, we don't count that as evapotranspiration. That's leached water. But it goes into the equation as water that leached. And then you do everything that you normally would do. You plant your crop on top of it, you irrigate it, you fertilize, you grow it just like the field next to it. And you're monitoring the weight the whole time. And there's a data logger here, and there's often a small spot. Somebody could put a laptop down here. It's not an area where you're going to work, but you might need to go down there to perform some repairs. You might need to go down there to collect the data, to get the data off the data logger, depending on how it's set up. Pretty interesting devices. And you've got soil probes interspersed throughout here. It's really a very expensive, tedious thing to make a lysimeter. And I'm going to take a quick break at this point.